Exercise 14E, trees and minimum connector problems. A tree is a network graph that has a relationship between vertices and edges. And when I say a relationship, I mean that the number of vertices, if I do something to it, I will get the answer to the number of edges that I have. So I've got these three graphs. I need something that's in common with those graphs, such that then when I've got the next few, so these ones here, these are not trees. So we need to find out what's in common. Why don't you have a go? Have a look at the edges, have a look at the vertices, and see what you think is in common. And then play this video when you want to check your answer. So, one of the things I would do is I would count how many I've got. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 vertices. And how many edges do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 edges. 1, 2, 3, 4. There's 4 vertices. 1, 2, 3 edges. 1, 2, 3, 4, 5, 6 vertices. 1, 2, 3, 4, 5 edges. So what's in common with them? Well, there's always one less edge than vertex. These ones are not trees. So let's go and have a look. 1, 2, 3, 4, 5, 6. There are 6 vertices. 1, 2, 3, 3 edges. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's 5 vertices. 1, 2, 3, 4, 5. There are 5 edges. So there's certainly no pattern there. So these ones don't have the pattern of one less edge than vertex. Is there any other properties about these graphs that aren't trees? Well, the other property, if we look at this one here that I've just highlighted, is that this one is not connected. All of the other graphs are connected networks. So the other property is that they're all connected. Hence or otherwise, state a rule that determines if a network graph is a tree. Well, if it's a tree, the number of edges should be equal to the number of vertices, take away 1. Or, if you like, edges plus 1 should be equal to the vertices, whatever one you prefer to use. So a minimum spanning tree is when I can find within a larger network a tree that has the smallest weights on them. So a reminder that a weight is just a number that we put onto an edge to indicate distance, time, or some sort of quantity. This is done on computers using a thing called Prim's algorithm. And thankfully in the study design, you don't need to worry about Prim's algorithm. And in fact, it probably makes things more complicated. I would suggest using some common sense. That will help you out with these sorts of questions. A minimal spanning tree of a connected weighted graph is a spanning tree for which the weight of the tree is as small as possible. It may be the shortest path, but doesn't have to be. So when you're trying to solve these, you just need to remember that the number of edges has to be the number of vertices take away 1. So let's look at example 2. The vertices represent school buildings and the edges represent footpaths. The numbers represent the distance in meters between the buildings. The school council has decided to cover some of the footpaths so the students can access any building during rainy weather without getting wet. What is the minimum distance that needs to be covered? So things that we need to remember is that the number of edges has to be vertices take away 1. And it also needs to be connected. So that's a good thing to remember as well. So in this case, the vertices that we've got, 1, 2, 3, 4, 5, the vertices equals 5. So therefore the number of edges has to be 5 take away 1, which is 4. My solution to this is to get your highlighter out and to just start by finding the smallest weighted edge. The smallest weighted edge in this example is 32. So we've tackled one edge. Then what I would do is I'd find the next smallest, which is 45. So that's 2 edges. I've got 2 more edges to go, and I need to connect everything. Then I find the next smallest, 50. And then I need to connect that first highlighted graph with the other 2 highlighted lines because I've only got 1 edge to go. And so I would pick the smallest number out of all of those, and that's going to be 62. So 32 plus 62 plus 50 plus 45. So that's going to be 94 plus 95, which is equal to 189, and it's all in meters. Have a go at the next couple of examples, pause the video, and then play it again to get the answers. So example 3, what is the total weight for the minimum spanning tree in this graph? So 1, 2, 3, 4, 5, 6, 7. There are 7 vertices. So the number of edges is going to be 7, take away 1, which is 6. So start with the smallest, and the smallest looks like it's 3. The next smallest is 4. The next smallest are the 2 5s. Now how many? I've got 6 edges to play with. So I've done 4 already, so I can only spend 2 more. So let's look at my next smallest line, that's 6. And I just need to get this last lonely edge in here, and it looks like it's going to be that 7 is going to be down there. So we've now got, or alternatively, yeah, so there we go. So this should be equal to 6 plus 3 plus 5 plus 4 plus 5 plus 7. So 9 plus 9 plus 12. 18 plus 12. So I'm getting 30 as my minimum spanning tree weight. Example 4, a maximum spanning tree is when we connect the largest edges rather than the smallest, but still using the same tree principle. The figure shown represents a telephone network connecting 9 towns. The weights represent the capacity of the telephone connection between the towns connected, that is, the maximum number of calls that can be made at the same time along the edge. A telephone engineer wishes to determine the maximum capacity of the system in terms of the tree connecting all the towns so that all the calls can be routed along the tree. What is the capacity? So we first of all need to get the number of vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 vertices, so the number of edges has to be 9 take away 1, or 8. So rather than finding the smallest lines, I'm going to find the biggest lines. So the biggest one, I think, if we look at it, it looks like that's 65. And the next biggest is going to be the 42. The next biggest after that looks like it's going to be 39. Then the next biggest after that is going to be a 36. Then we've got a 35. Then we've got a 34 and a 33. Now let's see, how many edges have I used up? Because I've still got this one vertex to go. 1, 2, 3, 4, 5, 6, 7. So hang on, let's just triple check here. Oh, and I've still got this vertex. I've got 2 vertices to go, and I've already used up 7 edges. Because then the next one would be 30. But oh no, I've got a vertex left over. So you'll notice here, I've got this 35 here, this 35, and we're already connecting this loop. So I really don't need that 35. So I can actually erase that 35. And what I'll do is because I need to connect this vertex, I need to find whichever edge has the largest number. In this case, it's 22. So unfortunately, our little system of just going with this sequence of numbers doesn't always work. That's why you need to remember always that a tree has to be connected, so you don't leave any vertices behind. So in this case, it's 22 plus 34 plus 36 plus 42 plus 65 plus 33 plus 30 plus 39 which I believe gets you 301 calls.